Welcome to this explainer. Today, we're diving into something absolutely critical for the future of computing. We are exploring QVector Decoder v3, which is an incredible piece of software addressing one of the most significant engineering bottlenecks of our time. It is all about bridging what is known as the quantum speed limit and laying down the essential software infrastructure we literally have to make fault-tolerant quantum computing a reality. So it all really starts with this one high-stakes question. Can classical software actually keep up with quantum hardware? You see, quantum computers operate on microsecond scale cycle times. They are blazingly fast, but they are also incredibly noisy. If our classical software can't decode the errors fast enough, the whole quantum system essentially collapses. At the end of the day, classical processing latency is the ultimate bottleneck. Okay, let's just jump right into our roadmap for today. We'll start with the quantum speed limit. Unpack QVector Decoder v3. Dive into its REST core and Python interface, check out the math and hardware acceleration, look at the sovereign researcher ethos behind it, and finish up with the future of QEC.
All right, part 1, the quantum speed limit. If you've been following the noisy intermediate scale quantum era, or NISQ, you know exactly what this is. We're talking about the microsecond scale cycle times of physical quantum hardware that classical error correction software simply has to match to achieve fault tolerance. I mean, if our decoders are too slow, quantum errors just pile up way faster than they can be fixed. The software must be flawlessly optimized to prevent this from happening.
Moving right along to part 2, unpacking QECTOR Decoder v3.
Believe it or not, getting your hands on this highly complex production-grade quantum tool really just starts with a basic terminal command: pip install qvector-decoder-v3. You can grab the entire project directly over at pypy.org/project/qvector-decoder-v3. It's built from the ground up to be instantly accessible to researchers. No massive corporate infrastructure required to get it running. 2,800. That's a pretty massive number, and it represents the unique installers this package saw in just its first 14 days out in the wild. And the best part? 0 reported issues. That incredibly rapid, smooth adoption really establishes the project's credibility right out of the gate. And it highlights a huge demand in the research community for fast, reliable tools.
Which brings us to part 3, the REST core and Python interface.
So how does it pull this off? Well, the performance relies on 2 distinct halves. Think of the Rust backend as the engine. It handles all the heavy lifting with native execution speeds, strict memory safety, thread-level concurrency, and those sweet, jill-free hot paths. Then on the other side, the Python front end acts as your steering wheel. It gives you a highly ergonomic API, 0-copy NumPy arrays, DEM parsing, and genuinely accessible tooling. It's brute force Rust speed married to everyday Python usability.
Stepping down into part 4, math and hardware acceleration.
Out of the box, QVector Decoder v3 gives researchers a lot of flexibility with 3 primary decoding pathways. First up, minimum weight perfect matching. That's your graph theoretic decoder for pairing defects. Second, union find, which is all about extremely low latency through near linear clustering. And finally, belief propagation with ordered statistics decoding, which is specifically built for handling correlated noise on quantum LDPC codes. Now, numbers talk, right? And these aren't just theoretical ideas on paper. They're backed by hard, verified metrics. While it easily matches the PyMatching standard for exact MWPM parity, the real standout here is a massive 35.7% reduction in logical error rate for belief matching at distance 5. Combine that with an absolutely incredible 98.3% optimal shots at distance 9, and you've got something really special. To handle those high-volume syndrome workloads, the software throws in a CUDA and OpenCL batch matcher. Basically, it processes batches of syndrome frames concurrently on parallelized GPU kernels. But here is the really mind-blowing part. It actually outputs bit-identical results to the CPU runtimes. You're getting the massive speed boost of hardware acceleration, but you aren't sacrificing a single bit of mathematical precision or consistency. Let's pivot to part 5, the sovereign researcher ethos. So here's a fascinating twist. This software wasn't built by some traditional corporate mega lab. It was actually created by an independent sovereign researcher named Guillaume Lessard, operating under the label IDEO One Productions. And their portfolio is wildly eclectic. Advanced QEC research and textbooks sit right alongside retro gaming development utilities, cyberpunk sci-fi literature, and industrial soundtracks. It is a massive contrast to your typical buttoned-up academic environment.
And you know, that unique background brings a really distinct, almost gritty attitude to the project. Just take this quote straight from the creator's GitHub discussion board. You installed it, now break it. I love that. After hitting thousands of downloads with literally zero reported issues, that slightly rebellious challenge just radiates supreme confidence in the software stability. But honestly, that confidence is 100% earned through what the project calls its artifact-backed culture. They operate on 3 strict rules. 1, never make baseless faster than X claims. 2, always run competitive scripts locally on the exact same machine to keep things totally fair. And 3, record and publish reproducible SHA 256 benchmark artifacts. This whole project relies entirely on rigorous, verifiable evidence over any sort of marketing hype. Total transparency is the priority here.
And finally, Part 6, the future of QEC.
So, what does this all mean? Will the quantum revolution be built exclusively by massive corporations, or will it be heavily driven by sovereign independent researchers? QECTOR Decoder V3 proves without a doubt that highly adaptable, incredibly performant tools can totally come from outside the traditional lab system, successfully bridging the quantum speed limit and pushing the entire field forward. It really leaves us to ponder what the future landscape of quantum tech is actually going to look like. Thanks so much for joining me for this explainer. I hope this inspired you to go check out the source material for yourself over at pypi.org/project/QECTOR-Decoder-V3.